exponential growth and decay problems are modeled using this equation, y equals ce to the kt power. In this equation, c stands for the initial value. Now, initial value, if we're talking about a radioactive decay kind of problem, then it might be the amount of radioactive substance that we start with. If we're talking about a population growth problem, then it might be the number of animals in a certain population that we start with. K is called a constant of proportionality. Y is the quantity or the amount that remains after a certain period of time. When K is positive, we have an exponential growth model, and when K is negative, we have exponential decay. Now, just as a sidelight to this, I want to point something out. We're going to look at the derivative of this and point out a certain relationship of the derivative to the original function. Now, just have a look at the derivative. It's not so much the case that we're going to be taking derivative in the problems that we're looking at, because we're not going to be doing that. But let me just show you this. If we take the derivative here, then y prime is equal to c times the derivative of this. And we're using the product rule, and the other part of the product goes out. But the derivative here, the dy dt of e to the kt, means it is, remember, e to the u prime is the idea. So here's the e to the u business, and the u prime would be the derivative of kt, which is just k. Now I can rewrite this as k times ce to the kt, but ce to the kt was the y that we started with up above. So we can write this as k times y. Now, if y prime equals ky, then an interpretation is that the rate of change in y is proportional to y. The rate of change in y is proportional to y. This is kind of a result of taking derivative. But you know, it's not so much the case that this relationship emerges from the original, even though we can see it that way. It is more the case that we start with this idea that the rate of change in something is proportional to the quantity to begin with, and then we could generate the equation that we started with. And I just want to point that out, because it's not always the case that equations emerge and then we have its derivative. A lot of times it's the case that we have a derivative idea and then we generate an equation whose derivative is this function. That is, the function that we start with up here is the function that we can take the derivative of in order to arrive at this. You see, and working backwards is a particular technique in calculus, and we'll talk more about it later. But this process will have a name and so forth. This is called a differential equation, and the original one is called the solution to the differential equation. And there's a whole family of problems that are involved with this idea. But I just want to point that out because it gives you a feeling for the nature of the way that the math develops here. Let's take a problem. This one says a sample contains 1 gram of radium. The half-life of radium is 1,620 years. How much of the radium remains after 1,000 years? Now, in problems like this, the general idea is to start with the general model, and then using information from the problem, we want to identify values for K and for C. Sometimes C is given and sometimes it's not. But just from the information up here, we can find those values. Now, with half-life problems, it is particularly easy to find the value for K. And here's how that's done. For half-life problems, you just put the time for half-life over here, and then in the y equals ce to the kt, after this amount of time, half of the original quantity remains. So this y, this remaining quantity, is 1/2 of the starting quantity, 1/2 of c. The c's go out, as I've indicated here, and now we have a relatively straightforward exponential equation. And we go into the logarithmic form. Let's see, the log then of 1/2 is equal to k times 1620, or 1620k. And then dividing on both sides by 1620, we find k to be this fraction. Punching the calculator, we find k to be approximately this long decimal. Now, with that information, we just come right back over here, and we're going to replace k with that constant. And we'd like a replacement for c as well. Now, it's telling us in this problem that a sample contains 1 gram of radium. So that's the the starting quantity. So C is 1. Now, if we didn't have a C of 1, and let me just write it as a general C just for the time being, and write this K in here, because I think it's important for us to realize, let's see, 4279T. Okay, I think it's important for us to realize that at this point in this problem, we could say, well, gee, how much radium would remain after 10,000 years if we started with 50 pounds? You see, how much radium would remain after 3,000 years if we start with 150 pounds? You know, or something like that. So we would have some kind of time-quantity relationship, and we put the starting quantity here and the time over here, and bam, we can grind out how much quantity remains after that period of time. Okay, let's do that here with 1 gram. Our starting amount is 1. And the time we're talking about is 1,000 years. So we just go y equals E to this long decimal times a time of 1,000. And it's just a button push here. It's just a number in the calculator, and we find that y is approximately 0.652 grams. Now, this was a decay problem. The graph would be a declining graph. Here's one that involves a population growth. It involves fruit flies, and these are a lot of fun because fruit flies tend to multiply like crazy. But we're not given the starting population of the fruit flies. We're only told that after 2 days there are 100 flies, and after 4 days there are 300 flies, and we'd like to figure out the number of flies in the population after 5 days. Well, once again, we need to build a model, and particularly we need the value of C and the value of K. And we can start that process just by using the general model and filling in information that we're given. Now, here's the general model, and the 2-day 100 fly business works like this. The time T is 2 days. The quantity after 2 days, you see the Y value is 100. So 100 flies after 2 days is what this corresponds with. And then over here, the information about 300 flies after 4 days, the quantity after 4 days is 300. The T is replaced with 4. Now, what are we going to do with these two models? It doesn't seem like we can get anywhere. Well, when you build two separate equations like this within the same problem, the idea is that you have a system of equations, and we're solving the system. And our basic method for solving systems like this is the method of substitution. So we'd like to solve for one letter and then substitute the information into the other equation. And that's basically the strategy that we use. It's pretty easy here to solve for C. If I divide on both sides by e to the 2k, then I find C to be equal to 100 over e to the 2k. Now I can take this information about C and I can just plug it into the other equation. You see, because I have a C here, now I have 300 equals, now in place of C, I'm going to put the information from over here. It's the 100 over e to the 2k power, and now I'm bringing down e to the 4k. You see, and at this point, I can actually solve for k. I've got a nice cancellation here, e to the 2k, e to the 4k. Gee, I have like bases. I'm dividing. I can subtract exponents, so it's e to the 4k minus 2k. Oh, that's e to the 2k. So and I can divide on both sides by 100. I'm running out of room here at the bottom of the board, so I'm going to go ahead and show that division. This is 300 over 100. And on the right, I have this cancellation opportunity, which gives me e to the 2k power. And now this becomes 3 over here, so I have 3 is equal to e to the 2k, and I go into the exponential form. I might as well show that. Let me come up here and show that process a little bit. What I've got down there is 3 is equal to e to the 2k power. And now I want to go into the logarithmic form, so I have ln. Now the base is e and it's understood here. The exponent is 2k and the number is 3. So ln 3 is equal to 2k. And if I divide by 2 on both sides, I find that ln 3 over 2 is equal to k. All right, here's my k value. Now I can find C relatively easily. I've got a number of models over there involving a C, and all I need to do is plug in order to find that value. And let's go ahead and do that. I've got the first model is 100 is equal to CE to the 2K power. Okay, now that I know what K is, K is ln 3 over 2. You see, and now this is just, all of these are constants. Even though E is here, it's a letter, and ln is here, these are just constants. These are numbers in the calculator. So all of this is just a coefficient of C. And so C then is, see, I'm going to divide by this coefficient on both sides. C is 100 over all of this business. E to the 2 ln 3 over 2. Actually, these will go out. So e to the ln 3. And we find C then, we approximate that value to be 33. I could use this exact value if I wanted to. But now I have a value for K and a value of C, and now I've built my model. So in the general model, I come over here, way over here, and here's the general model, and I just calculated that C is about 33. And the value of K is this value, and away we go with answering our question. The question was, how many fruit flies remain after 5 days? So I replaced T with 5, and I just punched the calculator to find this expression to be approximately 514. So 514 fruit flies remain after 5 days. Suppose we know that the balance in an account doubles in 6 years. If the interest is compounded continuously, what is the interest rate involved in this 6-year doubling situation? Well, we can figure it out by starting with the general model having to do with continuous compounding, and then fill in the information that we know. We know that under this doubling situation, the principal is the amount we start with, the amount after a certain period of time. Gee, if it doubles, then we have 2 times P, so 2P replaces A. And then the time is 6 years, and away we go with solving for R. Now the P's cancel here, and so we have this. 2 is equal to e to the 6R power. And going into the logarithmic form, ln 2 is equal to 6R. Dividing by 6 on both sides, we find that R is equal to ln 2 over 6. So using the calculator, we find that R is approximately this decimal. We change it into a percent, and this then is our interest rate. In this problem, a retail store has stopped advertising. And the advertising stopped, and after 4 months, here's what happens. The sales drop from 100 units per month to 80,000 units per month, and in that 4-month period. Now, if sales follow an exponential pattern of decline, what will sales be after another 4 months? Well, we need a model to generate information about this problem, and we build the model according to the given information. And once again, we start with our general idea and then put in information that we know. We know that the starting number of sales per month was 100,000. And after a 4-month time period, we end up with sales of 80,000 units per month. So with this information then, with this model, we can find K. And let's do that. We divide on both sides by 100,000, and over here we get 8/10. And then on the right, e to the 4K power. Now we go into the logarithmic form, so ln 0.8 is equal to 4K, and now dividing on both sides by 4, we find K to be this fraction, which is approximately negative 0.0558. Now that we have K, we rebuild our model from the beginning and replace K with that value. Here we go up here. So up here, we replace K with the value that we found for it. And now we know that the starting quantity was 100,000 units per month in sales, and we can figure out any number of things after a time period of 8 months. You see now, we're using 8 here because, remember, the initial information was that 4 months after the advertising was dropped, the sales dropped from 100,000 units a month to 80,000 a month. And now we want to figure out how many sales per month are going to occur after an additional 4 months. So that's 8 months after the beginning of this time period. And that's why an 8 is used here and not a 4. Remember, we dropped to 80,000 units after 4 months. We want to know how much the drop is after another 4 months, so that's why the 8 is here. Well, at this point, it's just using the calculator, and so we're multiplying 100,000 times e to this exponent, and we find the number of units per month sold to be predicted to be 64,000 units.